So good morning, everyone. I'm Kaushik Kumar Ram, and today I'll be presenting HyperSwitch, a scalable software virtual switching architecture. The other authors on this paper include Mehul Chadha and my advisors Alan Cox and Scott Rixner. We are from Rice University. Machine virtualization has become a cornerstone of modern data centers. It enables server consolidation as a means to reduce costs and increase efficiencies. It is also used to build, Hello. Oh, okay. It is also used to build many of the cloud-based server infrastructures that have become immensely popular over the last few years. Today, you see hundreds of such cloud solutions that use virtualization, as I've shown here. Now, virtualization has brought about some fundamental changes to the data center network. To explain this, I've depicted a rather oversimplified data center network in this figure. Here, I've shown a bunch of network switches that are connected to each other in a hierarchical fashion. Now consider a packet which reaches the top level switch from outside the data center. This packet is switched multiple times at different places before it reaches its final destination, which is a server sitting on some rack in the data center. Now when you add virtualization to this picture, essentially each server is going to host a number of virtual machines or virtual servers. And as a result, the packets have to be switched one more time before they reach their final destination. Fundamentally, the communication endpoints within the data center are now virtual machines and not physical machines anymore. And therefore, the data center network now extends into the server. Our claim is that this virtual switching component is going to increasingly become a performance-critical piece in this architecture. This view is supported by some recent trends in the data center. Today, inter-server traffic, or the so-called east-west traffic in the data center, is already significant. For instance, a single Amazon EC2 request causes as many as 100 servers in the data center to exchange messages between them. In fact, a recent data center study has shown that as much as 80% of the traffic never leaves a single data center rack. This is, of course, thanks to the ever-increasing processor core counts on servers. The number of cores on a chip is expected to reach 256 or even 512 by the end of this decade. As a result, the server VM density, which refers to the number of VMs that can be packed into a single server, is also going to go up. Now, if you assume that the related application VM instances are going to be smartly co-located to run on the same physical server, then you can imagine that in the future, the majority of the traffic never leaves a single physical server. What all this means is that we need a high-performance virtual switching component inside these virtualized servers. Toward this end, we present the HyperSwitch architecture in this paper. HyperSwitch is a highly efficient and scalable software-based switch for virtualization platforms that support driver domains. It combines the best of the existing software architectures for achieving better performance and accelerated inter-VM networking, which is really the focus of this paper. It also presents a series of optimizations, including preemptive copying, virtual machine state-aware batching of packets, and dynamic offloading of packet processing. It should be noted that these optimizations are not specific to HyperSwitch. In fact, they can and should be a part of any virtual switching solution that aims to deliver high performance. The outline for the rest of this talk is as follows. First, I'll be providing some more background information to set the context. Then I'll provide an overview of our design and motivate the new architecture. This will be followed by the various optimizations. Then I'll describe our prototype implementation and present some experimental results from an evaluation of this prototype. And finally, I'll summarize our conclusions. Now, if you look at virtualized servers today, the software-based solutions are most widely used to support networking. This is in part due to the flexibility and the rich set of features they offer. The software-based solutions can be broadly classified into two kinds. On one hand, there is the hypervisor-based I/O model, where the virtual network interfaces, along with the device drivers needed to access the underlying devices, are implemented inside the hypervisor as shown in this figure. And the hypervisor exports the VNIX to the guest domains. The VMware ESX server, for example, supports this I/O model. Now, on the other hand, there is the driver domain-based I/O model. Here, the device drivers that are needed to access the underlying devices are hosted inside a dedicated separate VM called as the driver domain. And the driver domain also implements the VNIX. Arguably, this model supports better fault isolation and in general is more reliable than the hypervisor-based I/O model I showed previously, because studies have shown that device drivers are one of the main sources of operating system bugs. So by sandboxing the device drivers to run inside a separate domain, any potential faults can be contained. Further, this also reduces the size of the TCB, which is the trusted computing base. This is the minimal set of hardware-software components that are critical for the security of the system. For instance, hypervisors like Zen that use driver domains are quite lean. So while driver domain offers these nice properties, it also incurs significant overheads. Previous studies have identified memory sharing during I/O operations as one of the major sources of overhead. These overheads are incurred when packet buffers are shared between the driver domain and the guest domain in order to transmit or receive packets. So in this work, our goal was to really look for ways to preserve these nice properties which derive from the use of driver domain and at the same time achieve scalable and high performance. Now, if you consider both these existing software virtualization architectures, the VNICs which are exported to the VMs, the virtual switch that is used to forward traffic, and the device drivers are all implemented inside the same software domain, be it the hypervisor in the first model or the driver domain in the second model. This co-location is purely a matter of convenience since packets that are received at a virtual network interface have to be switched before they are handed either to another virtual network interface in the case of inter-VM traffic or handed to the device drivers for external communication. Instead, in this paper, we propose HyperSwitch, which changes this conventional design. So in this architecture, we move the switch into the hypervisor, as in the hypervisor-based I/O model, but retain the device drivers to continue running in the driver domain, as in the driver domain-based I/O model. This is shown in this figure. The virtual network interfaces are also implemented inside the hypervisors, so the guest domain now talks to the VNICs in the hypervisor. As a result, inter-VM traffic is handled completely within the hypervisor, but external outgoing traffic is forwarded first to the hypervisor and then through the driver domain outside the server. And incoming traffic goes in the opposite direction. It should be noted that the packets are not pushed through the network stack in the driver domain. They are merely delivered to the device driver for external communication. Now, there are some nice features to this architecture. It has been optimized for both latency sensitive as well as bulk traffic. We have implemented some novel optimization that take advantage of the integration of the switch within the hypervisor and its proximity to the scheduler. Specifically, it uses the knowledge of when and where a VM is running to optimize performance. Further, the virtual switch implementation is distributed to obtain the best possible performance. In particular, the entire virtual switch is not implemented inside the hypervisor. Instead, the control and the data planes are separated as shown in this figure. So the hypervisor only implements the data plane of the switch. The control plane is implemented inside the management domain, such as the domain 0 in Zen. The main benefit from this high-level architecture is that by moving just the switch's data plane inside the hypervisor, we ensure that the size of the hypervisor is not inflated a lot. As I mentioned earlier, one would like to keep the size of the hypervisor and thus the TCB as small as possible. But putting just the data, so implementing the entire switch inside the hypervisor was not an option for us. But putting just the data plane of the switch inside the hypervisor is okay because data plane is relatively much smaller as compared to the control plane. For example, the data plane of OpenVSwitch, which is a software switch for commodity servers, has about 5,000 lines of code, whereas its control plane has about 90,000 lines of code the last time we checked. Now, we use a flow-based interface for the communication between the control and the data planes. The way the packets are switched here is similar to how packet switching is done using OpenFlow, for example. I'll briefly describe the procedure here. The packets are switched in 3 steps. Now, when a packet is received by the switch, first the packet flow is identified by parsing the packet headers, and this flow is used to look up a software flow table. Now, if the flow table lookup is successful, then it identifies a flow rule and a corresponding action to be performed. The action could be something like forward the packet to port number so-and-so, which in turn identifies the destination virtual network interface, or maybe drop the packet. Therefore, if the lookup is successful, you can think of this as a cache hit. Then the packet is handled completely inside the data plane in the hypervisor. Otherwise, the packet has to be forwarded to the HyperSwitch control plane software, which is running in the management domain, where a new flow rule is synthesized and installed into the flow table in the data plane. And finally, the packet is re-injected into the data plane so that it can be switched and forwarded to the correct output port. In the following slides, I'll describe the design of HyperSwitch. I'll start with the basic packet processing first, and then I'll explain the various optimizations that were implemented on top of this. I've depicted the steps involved here using both the figure at the top as well as a timeline at the bottom. And let's assume that the destination domain is blocked when the packet is being transmitted. Now, from the HyperSwitch perspective, packet processing begins when a packet is queued by the transmitting VM in its virtual network interface. Then the transmitting VM issues a hypercall in order to enter the hypervisor, where the packet is removed from the virtual network interface. Please note that although I have showed the packet to have moved from the guest domain to the hypervisor, the packet is not actually copied on the transmit side. This is because the hypervisor can directly access the packet in the transmitting guest domain's memory. Then the packet is pushed into the data plane of the switch, where it is switched using the flow-based approach I described in the previous slide. Then the packet is placed in the internal receive queue at the destination virtual network interface, which is identified using the output from the flow table lookup. Then the destination VM is notified. This unblocks the receiving VM, and subsequently the receiving VM enters the hypervisor. It copies the packet into its memory, and when it returns back, the packet is ready to be pushed into its network stack. There are two main benefits from this design. First, there are no memory sharing overheads since packet buffers are never directly shared between two VMs or domains. Second, a subtle benefit is that it allows for better I/O resource usage accounting. This is a huge problem in traditional driver domain model because it's extremely hard to account for the cycles which are consumed in the driver domain and attributed it back to a specific virtual machine. Instead, in this architecture, by default, packet switching is performed in the transmitting VM's context, and packet copying is performed in the receiving VM's context. Therefore, special mechanisms are not needed inside the scheduler to account for the resource usage during I/O operations. Further, there is minimal processing which happens in driver domain because it is used only for external communication. Next, I'll describe our first optimization, which we call preemptive copying. It is based on the simple observation that when notifying a virtual machine, it requires hypervisor intervention. So we preemptively copy the packets to avoid the hypercall on the receive side. Now, if you look at the timeline at the bottom, after the receiving VM is unblocked, it immediately copies the packet, and when it returns back, the packet is ready to be pushed into its network stack. The primary benefit from this optimization is that we reduce the number of hypercalls on the receive side. Hypercalls are expensive operations. So by saving one hypercall on every packet, we make packet delivery much more efficient. And further, we also reduce the packet processing latency. The next optimization we implemented is batching. Here, the idea is to delay the packet processing so as to amortize the per packet overheads across multiple batched packets. We implemented batching both on the transmit as well as the receive side. The batching is driven by two parameters, a timer period and a packet threshold. So the packet processing is delayed either until the timer period elapses or the packet threshold is reached. This is similar to how interrupts are coalesced in network cards, for example. But there's some novelty to the way it has been optimized for this architecture. For instance, if a packet is destined for a virtual machine that is currently blocked, then it is notified immediately so that it can be woken up and it can start processing the packets. This is, of course, possible thanks to the easy access to the scheduler to determine if a VM is running or not. We get the following benefits from the batching of packet processing. First, we reduce the number of hypervisor entries on the transmit side. We reduce the number of notifications on the receive side. Further, batching typically increases the packet processing latency, but we reduce this effect at least for request response traffic by processing the first packet of a batch immediately, both on the transmit as well as the receive side. The final optimization is the offloading of packet processing. Now, in the design so far, the packet processing happens only in the transmitting or receiving VM's context. So we wanted to see if we can further increase concurrency by performing some of the packet processing in parallel on other processor cores. We achieve this by dynamically offloading some of the packet processing to just the idle cores in the system. We use a lightweight mechanism for offloading packet processing without involving the scheduler or performing any context switches. Again, if you look at the timeline at the bottom, it shows how this works. Let's say we have an idle core which is currently blocked. And let's say the receiving VM is busy processing its packets in the network stack or doing some application work. And let's also say that the transmitting VM has already entered the hypervisor and switched the packet. So we know what the destination VM is. Now, at this point, the offload mechanism kicks in, and it chooses the idle core, suitable idle core, and wakes it up. The idle core then copies the packets, and it also performs any other packet switching tasks as a side effect. And then the idle core is halted until there is more packet processing to be done. Eventually, let's say the receive timer goes off. This receive timer comes as a part of the batching mechanism I explained earlier. And this, in turn, notifies the receiving VM. And the packets are now ready to be pushed into the network stack. It should be noted that this mechanism is also CPU cache aware. As you all know, in modern processors, the CPU caches are often shared at various levels between multiple processor cores. And this offloading mechanism has been optimized to take advantage of any CPU cache locality. For instance, if the processor cores running the receiving VM and the packet copier shared a cache, as shown in this figure, this can benefit performance since the packet data will be brought into the cache when the packet is being copied, and subsequently the receiving VM can directly access the packet from its cache when it is processing the packets in the network stack. So now that we have seen how HyperSwitch works, I'll briefly talk about how we built a prototype of HyperSwitch. It was implemented in the Xen virtualization platform using OpenVSwitch. This figure, OpenVSwitch is a multi-layer commodity software switch, and this figure depicts how OpenVSwitch was used to build this prototype. Today, when OpenVSwitch is used in Xen, the entire switch is run inside the driver domain. Its control plane is implemented in the driver domain's user space, and its data plane inside the driver domain's kernel. So what we did was we took the switch and we ported the data plane along with some essential libraries to run inside the Xen hypervisor. Further, the unmodified control plane was run inside Xen's domain 0, which is the management domain. Further, we also implemented a glue layer in the kernel, which forwarded the various commands from the unmodified control plane to the data plane, which is now running inside the hypervisor using newly added Xen hypercalls. We also implemented a new para-virtualized network interface, which used circular buffers to implement the transmit and receive rings. This is similar to the virt.io interface, which is used in KVM, for example. The offload mechanism used a simple message passing interface to communicate with the idle cores in order to offload packet processing. And the interprocessor interrupts were used to wake up idle and halted processor cores in order to offload processing. Now, once we built this prototype, we used this to do a performance evaluation of this architecture. In this evaluation, we studied both inter-VM as well as external network performance. We also studied HyperSwitch's performance scalability. And we compared its performance to the performance of the original OpenVSwitch when run under Xen's and KVM's default network I/O architecture. So here are some details on the default network I/O architecture as it is used in Xen and KVM today. As I mentioned earlier, Xen uses a driver domain I/O model. Here, the backend driver called netback, which is implemented inside the driver domain, implements the virtual network interfaces. The netback is multi-threaded, and as shown in this figure, there is one kernel thread for every vCPU in the system. And the VNICs are bound to one of these kernel threads. KVM, on the other hand, uses the hypervisor-based I/O model. Its vhost-net architecture, the vhost-net driver implements the virtual network interfaces. Similar to netback, it is also multi-threaded, but unlike netback, there is one kernel thread for every VNIC in the system. The server configuration used in this evaluation is summarized in this table. Essentially, we used an AMD server with two 2.2 gigahertz Opteron processors, 32 cores, 64 GB of memory. The domain 0, the driver domain, and the guest VMs all ran a recent para-virtualized Linux kernel. Due to lack of time, I'm going to be showing only a few results today. In one set of experiments, we set up network traffic between a pair of VMs running on a server. We used TCP stream-based traffic, and we measured the throughput across several TCP payload sizes. In these experiments, HyperSwitch performed much better than Xen and KVM for larger packet sizes between 4 and 64 kilobytes. On average, it was 56% better than Xen and 61% better than KVM. In another experiment, we used UDP-based request response traffic to study packet processing latency. Here we measured the number of transactions per second. This in turn indicated the average latency during packet processing. Again, in these experiments, HyperSwitch achieved higher transactions per second than KVM and Zen across all payload sizes. This indicated lower packet processing latency. On average, it was 117% better than Zen and 222% better than KVM. In one of our scalability experiments, we varied the number of pairs of VMs concurrently communicating with each other from 1 to 16. So at the last point in this graph, we had 32 VMs running in the system. Further, we also pinned all the VMs, vCPUs, and the backend processing threads to avoid any scheduling artifacts. The pinning was done such that the processing was evenly distributed across all the processor cores in the system. Now, if you look at the performance curves under Zen and KVM, you will see that it scales up to 4 pairs of VMs before it starts to flatten out. But if you look at HyperSwitch's performance curve, first of all, it achieves much higher peak throughput of nearly 81 gigabits per second as compared to 31 under Zen and 47 under KVM. Now, if you look closer at HyperSwitch's performance curve, you will see that there are 3 regions here. Between 1 and 4 pairs of VMs, there is near perfect scalability. This is because in these cases, there was always an idle core to offload packet processing, and the offloading could be done optimally with respect to CPU cache locality. Between 4 and 7 pairs of VMs, there was reduced scalability. This was because as the system got busier, while the processing could still be offloaded, it could not be done optimally with respect to CPU cache locality. Beyond 8 pairs of VMs, it did not scale further. But at the same time, it did not degrade the performance as well. The paper provides more information on these experimental results. It also presents results from another scalability experiment where we had an all-to-all communication between all the VMs running in the system. And we observed similar performance curves there as well. And if you're further interested, my thesis has even more results. So in conclusion, there is a need for efficient and scalable inter-VM communication in virtualized servers. So we designed HyperSwitch. HyperSwitch combines the best of the existing architectures by integrating the switch into the hypervisor and retaining the device drivers in the driver domain. We also implemented several optimizations which enable efficient and highly concurrent packet processing. We built a prototype and evaluated this architecture. The evaluation showed that HyperSwitch achieved our design goals and performed better than Zen and KVM's default network I/O architecture. Thank you. I'll be happy to take any questions.
I have a quick question, Günther, Cornell University. Could you describe the resulting TCB of the system at the end of the day? How big is it? And for a set of VMs, that assuming that all of them use the network, what's the TCB like?
So the TCB size is determined just by the size of the data plane. So it is not sort of proportional to how many VMs are running the system, right? And so we haven't measured the actual data plane size with respect to what the hypervisor size is, but I would say it's less than 5% increase in the size of the hypervisor, but I don't have the exact number.
Okay, great, thank you.
Rick Farrow. So do you think that the performance gains that you're getting are because you're avoiding copies?
So we have to do the packet copies on the receive side, right?
Right,
so
right. But you have one copy instead of, say, 2 or more copies, right? Or are you actually avoiding any copies by doing this?
So we are not, if you compare it to the default architecture in Zen, for example, we are not actually avoiding any copies, right?
Okay.
The same number of copies happens both in Zen as well as in HyperSwitch, right? The copy happens only on the receive side. On the transmit side, you just share the packet buffers, and that's what we do as well. And so the performance enhancements really come from the fact that if you compare it to Zen, we don't do any memory, the memory sharing overheads are not there. And it's mainly because of these optimizations which we implemented. You can really tune the system to do the copies at the right place. If you know exactly what the receiving VM is, and if you have an idle core, make sure they share a cache, and you're going to see these performance.
Okay, thanks.